Okay, guys, so basically, as I mentioned, my little study guide here that I'm going to go through, it's not the one you're doing, but every set should be pretty similar to the sets that you guys have. And we've already been through all this, so you guys may not even need the video. Just providing this for your guys' extra help if you get stuck on a particular problem. So once again, I tried to make them look as much as I possibly could like your actual worksheet. Let's go ahead and get started. Okay, so the first problem, what we're going to do is we're going to rewrite each one of these equations here in exponential form. So remember what we talked about, guys, what the definition of a logarithm is. If you have an exponential function, a logarithm is the inverse of an exponential function. So over here, my base is a, so the log's base is a, but the input and the output get swapped. Okay, and so that's what a log is. Okay, so in this case, they want us to rewrite this as an exponential function. And so here's my base, so it's going to be 16 to the power of this output equals that input. There you go. That's it. All you have to do is rewrite it in exponential form. Next question. All right, we talked about ln as well. What ln is basically just a special log. It's a log with a base of e, which is the Euler's number that we talked about when we talked about exponential functions. And why do we care about this? Well, we talked about that as well. It's just because e is really a very natural occurring base when it comes to talking about exponential growth and logarithms, and so it's called the natural base. And you don't have to show your work in the way that I do, but just to kind of keep things simple, I'm going to rewrite this as log base e of t equals x. Now that I've done that, if I want to change this into exponential form, it's going to be e to the sixth power, equals t. Okay, and that's that. Continue here. Technical difficulties here, just a second. All right, so next question. Log 7n. So you'll notice that there's a number missing here. In this case, the base is not written. And when the base is not written, we assume that it's a base 10. That's called the common log. In that case now, if I wanted to rewrite that in exponential form, it would be 10 to the nth power equals 7. Okay. Go ahead and move on to a different set of questions. Now, the opposite, we're going to be changing exponential functions into logarithmic functions. So, in this case, we're going to start by writing the word log. 7 is my base of the log. 49 becomes my input because over here it was my output. And the 2 becomes my output. And that's it. There you go. Go ahead and move on to another one here. 10 to the 5th power equals 10,000. So log base 10 of 10,000. Okay, now just so you guys know, the answer won't look like that though. It'll look like this, because when it's a common log, we don't write the base. Let's go ahead and take a look at number 6 here. So once again, we're going to have log, in this case base e, of the output j equals the input. And once again, a log base e, though, is written in a special way. It's written like that. There's our final answer. All right, now we're going to get into evaluating expressions. So let's go ahead and review some log properties really quick here. First of all, we talked about this log property. Anytime these two numbers, the base and this number here, which is called the argument, match, the answer is just going to be 1. Okay. We also talked about another property where if the argument has an exponent on it and the argument matches the base, the answer will just be that exponent. Another thing that we talked about was something that's kind of like that. It just looks a lot different, but it's actually quite similar. This one, anytime you have an exponential expression where the base of that exponential function matches the base of the log, and that log is a power of that number, then basically these act like opposites and just cancel out. Same thing here. These are like opposites, cancel out. And a final second to final property we learned was this. Anytime you have a 1 in the argument, the answer is 0. And another thing that we learned was that no matter what number you have here for your argument, the b always has to be greater than 0. It can't be 0 and it can't be negative. So just reviewing some stuff that we learned a little while back. Now, when it comes to a problem like this, what we learned, we learned quite a few ways and two different ways to solve this. I'll go ahead and stick with one of them though. What we learned was we want this base to match this base. So the first thing that we did was we changed that 27 into a 3 to the third power. Now that the bases match, these cancel out and the answer is just 3, the exponent. Okay. Now in this case, we don't like fractions, right? So something we talked about a little while ago was how to change those fractions. And so 1 over 16 can be rewritten as 16 to the negative 1 power. A negative 1 power is just a reciprocal, which is what would make it 1/16. It's not necessarily just because there's a 1 on the top and that 1 becomes negative. Not how it works. The idea here is that that 16 has a first power on the bottom, and then if we were to move it up to the top, the power becomes negative, and this 1 just kind of can be ignored because when you multiply anything by 1, it just stays the same. Anyway, this is the outcome. Now the next thing we want to do is, like the last problem we did, is we want to get those bases to match. So instead of 16, I'm going to change that to 4 squared. And then we're going to multiply those powers together, and we end up with, and using one of our log properties, anytime the base matches the base here, those eliminate, and we're left with just the power as our answer. So there's that. Let's see. We also talked about square roots. Now, when it comes to square roots, or not, in this case, it's actually not a square root, it's a fourth root. There's a number inside, and that number on the inside has a power on it. In this case, it's not written, but we can assume that it's 1. Now, what we're going to do first is we're going to change this from a radical expression into an exponential expression. Instead of having a root expression, we're going to change it to an exponent. The way you do that is this number is our base number, 25. This is going to be my numerator, and the 4 is going to be the denominator, and the 1/4 is the power of 25. Okay. Once we do that, the next thing we do is we get the base of the log to match the base of this exponential expression here. And so we have log base 5, and I'm going to change that 25 to be 5 squared. Okay. And once again, you're going to multiply this 2 with the 1/4. So how do you do 2 times a 4th? Well, think of that 2 as 2 over 1, multiply straight across. 2 times 1 and 1 times 4 is 2/4, which reduces to 1/2. And so this expression simplifies to be 5 to the half power after we multiply the 2 and the 4th together. And then these cancel, and we're left once again with the fraction answer, the exponent. All right, here's another one. Now you'll notice on this particular problem, the base isn't written, but when that happens, as we talked about earlier, that's the common log, and its base is 10. So we have another fraction problem. We talked earlier about how to deal with that. The way you deal with that is you take this number and you're going to write the denominator and give it a power of -1. And then those cancel, and the answer is In this case, my argument is negative, and we talked about how the argument cannot be anything that is, well, the argument has to be greater than 0. So it can't be 0 and it can't be negative. So in this case, the answer is no solution. One of our other properties that we looked at, we saw that no matter what the log is, if your argument is 1, by the way, if you wanted to rewrite this, you could rewrite it like this. But if your argument is 1, then the answer is 0. Okay. In this case, once again, remember the argument has to be greater than 0. It can't equal 0, so we have another no solution problem. This one looks weird, but if we rewrite the ln as a log base e, which is what it is, we can see it's just the rule where those cross off, and the answer is 7. And then we have one of these guys here. The 10 crosses off the log because they both have the same base of 10. Remember, if the log doesn't have its base written, it's a 10. So those just cross off, and we're left with 6 as the answer. So this is just review. I know I'm plowing through it pretty quick, but I'm just trying to get your guys' brains back in gear here for next week. Start moving into our new lessons. So, okay, now for the next sets of this, and this is our last couple problems we'll be working on. We also learned some other properties. So here they are. I'll write them once for you. Log A plus log B. So long as these two logs have the same base, in this case I'm just making them base 10, you can actually put those two logs together as one log and multiplying those arguments together. We also talked about a similar rule involving subtraction. Subtraction, instead of becoming multiplication, actually becomes division. Now the order matters. The one that comes first has to go on the top, and the one that comes second has to go on the bottom. And then a third rule that we learned on that day, which I think was our last day in class, was that if you have a log and that number has a power on it. Now, remember, this looks a lot like the rule that we learned here, right, earlier? Don't they look kind of similar? And these canceled? Well, the reason those canceled is because log base A is the opposite of a base of A with an exponent, so they cancel each other out. But in the case that I'm looking at right now for this problem on the right here, is this log has a base of 10 on it. That does not match the A, so I can't just cross those off. That's a no-go. You can't do that. Okay? But what we can do is a different property. And that property tells me I'm allowed to take this exponent and move it up to the front, so it would look like this. Okay? And that you can do that property even when the bases don't match. So let's go ahead and apply these properties to solve a couple of different problems here. Just a minute. For a second. Okay, back to where we were. Sorry, I need to take a little break there for a minute. Okay, so let's apply these properties. So first of all, what we want to do is we want to condense this expression down into one log. We don't want two. So the first thing we're going to do is we're going to use that third property we talked about. You see how there's a number in the front of the log? Well, that number can become a power on the argument. Like that. Same thing here. That 4 can become a power on the 7. That. Now the next thing is you notice we have two logs that are being subtracted now. And as we talked about the subtraction, you can put those together as one logarithm if you take the first one and make it a numerator of the second argument. So there's your final answer for that. Leave it like that. They're not going to ask you to do 8 to the 12th power. That number is ridiculously big. There's no point in doing that. They'll just leave it like that. All right, moving on. Let's take a look at this one. Something else that we saw in class that day was this weird thing here where you have denominators here. So the first thing that we talked about when we did that was we said, well, let's rewrite it. Instead of writing this as log base 5 of a over 3, let's write it as 1/3 times log base 5 of a. That's the same thing. Dividing something by 3 is the same thing as multiplying it by 1/3. And so we're just going to rewrite it in friendlier terms. You'll see why it's friendlier in a moment. If you remember. Okay, now next what we're going to do is we're going to take this multiplier and it's going to become a power on the a. First log's going to stay the same. Nothing to do there for now. Same thing here. That's going to become a power on the b. Now notice this. These two logs here are being added. And what we talked about, when two logs are being added, you take their arguments and they get multiplied together. And then we still have this one over here as well. But guess what? It's being added also, so we might as well as just do the same thing again, right? So now we're going to take this new expression and put it with that one. Running out of space here. We have log base 5. So if I put this, multiply this with this, we end up with c a to the 1/3 and b to the 1/3. Okay. So I doubt they're going to leave the answer like that, just so you guys know. Here's what I think they're going to do. Space here. All right. First of all, I think they're probably going to change these back into radicals, right? That 1/3 power, kind of the opposite of what we talked about earlier. This is your root. The denominator represents what kind of a root it is. It's the third root. This is the number that goes inside. And this number is the power on the a. Now, if you have an a to the first power, there's really no point in writing the 1, so we'll leave it like that. Same thing here with the b. Be written like that. And since they're both cube roots, you can put those together as one big root, that. So my guess is that's how the answer would look. Okay. All right, moving along. All right, now the last few problems we're going to look at, 18 through 21, they're the opposite. Basically, the problems are one logarithm, and we want to split it apart into multiple logarithms. So in this case, before we begin, we're going to use a property of exponents here. If you have something being raised to a power, that u has a first power, the b has a third. So when you raise a power to a power, basically you're going to multiply the powers together. So it's going to end up being 1 times 5 is going to be 5. So instead of u to the first, it's going to be 5 now. And 3 times 5 is going to be 15 for the b. Now, in this case, notice how we have two variables being multiplied together. So that's the property where you can rewrite that as two separate logarithms that are being added. And one other thing they're going to ask us to do is to apply that last property where the power now is going to be moved to the front. So as you guys can see, we're just doing the exact opposite of what the last few problems were about. And that's your final answer there. So they want you to basically get the v and the u by themselves inside the log, and everything else needs to be separated. Okay. Let's go ahead and move on to another one here. So first of all, we have a w to the third being multiplied with a cube root u. First thing that might catch your guys' eye is the fact that there's a cube root there, and as you know, we've been kind of accustomed to changing those into powers now, right? Next thing we're going to do is, since we have two things being multiplied, is we're going to rewrite that as two separate logarithms that are being added. The next thing we're going to do is we're going to apply that third rule that we talked about at the beginning of this set, and we're going to move those to the front. It's going to be 3 log 9 w plus 1/3 log base 9 u. And just so you guys know, once again, they're not going to write this thing like that. What are they going to do instead? They're going to take this 1/3, and instead of writing it as 1/3 times log, they're going to write it as log over 3. Okay, and so there's your final answer. Okay, next question. Number 20. Once again, they want us to expand this thing out. So we want the a and the b separated from everything else. First thing we're going to do is we're going to notice that there's a fraction here, and that matches that second log property that we talked about at the beginning of the set. So it's going to be log base 5 of a to the third, the one on top comes first, minus log base 5 of b to the second. And then once again, the powers go to the front of the logs, and we should be good to go. All right, next question and last question, I believe. All right, in this case, we have just one giant square root. Now, how do we handle that? You have more than one letter under a square root. First of all, we have x times y times z, and instead of writing that as a square root, notice that all of these are being raised to the first power, and when you have a square root, the root is a 2. So we're going to rewrite that as a 1/2 power. Now, since I want to get the x, y, and z separate, I'm going to distribute this power to all of them separately. Notice all three of them are being multiplied, and so that reminds us of that first log rule that I shared with you guys at the beginning of this set, where you can rewrite these as 3 separate logarithms that are being added together. Finally, we're going to take these powers and we're going to move them to the front, right? And once again, they're not going to leave those fractions in the front like that. They're going to rewrite it like this. And so here's how your final answer will look. Instead of 1/2 in the front, they're just going to put it over 2. There you go. So there you guys go. Just a kind of little refresher of all the stuff that we've talked about with logs prior to our little break there. And next week we're going to start learning some new stuff. Go ahead and do your worksheet for some extra credit and be ready for some new stuff next week. All right. See you guys